In an earlier video, I talked about quantitative designs and I focused specifically on non-experimental designs. In this video, I will cover experimental designs. So just the textbook definition of an experiment is a scientific investigation in which the researcher manipulates one or more independent variables, controls any other relevant variables, and observes the effect of the manipulations on the dependent variable. I mentioned before that there are specific types of experimental designs, some of which will enable the researcher to establish a cause and effect relationship between their independent and dependent variables, but not all of these will. So in the next few slides, I will refer specifically to pre-experimental studies, quasi-experimental studies, true experiments, and small n or single subject studies. And in doing that, I'm going to use some notation that was introduced by Campbell and Stanley, who were some really influential scientists in writing about different experimental designs and quasi-experimental designs in particular. And they used the notation scheme where R refers to random assignment to groups, a dotted line refers to no random assignment, and what are referred to as non-equivalent groups. When we randomly assign to groups, we're doing that to hopefully end up with some groups that are considered to be the same or equivalent. So by not randomly assigning, we have non-equivalent groups. X refers to the experimental condition being introduced. O refers to observation, and you'll see a couple examples of what this actually looks like. But when you have multiple rows of notation, each row refers to a different study group. So let me just give you an example of what I'm talking about to make this a bit clearer. So this is a notation for a true experiment where you randomly assign participants into two different groups. So that's why we see two different rows of symbols here. So in the top row, we've randomly assigned to that group, then we take an initial observation, which is O1, and then we implement our experimental condition, which is X, and then we take a post observation, so O2. In the second row, this is what we'd refer to as the control group. So basically the exact same as the first group, except not being exposed to the experimental condition. So that just kind of gives you an introduction to the notation scheme that I'll be referring to throughout this video. So pre-experimental studies are studies that involve either no comparison group or no baseline measure. So in the first box you see on the left, it's just one group, they're getting the experimental condition, and then you're observing them after that. It doesn't really provide a whole lot of information if we do this because there's no comparison group in this case. In the second design you see in the middle, it's also one group, but in this case there is a pre-condition as well as a pre-observation as well as a post-observation after the experimental condition is introduced. And at least from that we can see whether there's a change in whatever it is we're measuring. So you can think of O as like the dependent variable and X as like the independent variable. So with, like I said, with the second option, we can at least see whether that dependent variable has changed in response to the independent variable. But still, we can only take limited information from this design because, again, there's no comparison group. And in the third example on the right-hand side, there is a comparison group. So there's basically like a control group here in the bottom row. But because of the dotted line, that's indicating that we haven't done random assignment, we don't know if these two groups were the same from the beginning, and we haven't taken a pre-observation to basically be able to test whether the groups were the same in terms of the dependent variable before the study began, before the experimental condition X was introduced. So those are pre-experimental studies, no comparison group or no baseline measure. Quasi-experimental studies, they typically will have different conditions or groups for comparison, but there's no random assignment. And that's what sets them apart. That's what differentiates them from a true experiment, whereas we'll see there is going to be random assignment. So in quasi-experimental studies, you might have something like the example on the left, where you basically have a pre and post observation, you have a control group and an experimental group, but those groups are already existing groups. So maybe it's like two sports teams and we're going to compare them, but we're using intact groups. We haven't randomly assigned, half of our participants to one group or the other. In the example on the right-hand side, this is a design that I often see in master's thesis projects where you have one group of participants and you have each of those participants taking part in a number of different experimental conditions. So maybe it's some type of pre-performance routine for sports psychology. Maybe it's some type of recovery activity after exercise, if you're in strength and conditioning or exercise physiology. And you're basically looking at some outcome in response to each of those, in this case, three conditions. And you notice O0 is actually referring to like a baseline measure of your dependent variable. So you can basically compare the response after each of those interventions with the initial baseline measure. So these are quasi-experimental studies. True experiments involve random assignment to different groups. And then after you randomly assign, you manipulate one variable, which is considered to be either the treatment, intervention, condition, lots of different terms we can use to refer to the X variable, while holding all else constant. And by holding everything else constant, then you can make a reasonable assumption that whatever you're observing in the dependent variable is in response to the independent variable X. So in the box on the left at the top, we have random assignment into a treatment group and a control group, and there's just an observation after the experimental condition is introduced. The box below that is basically the same, except in addition to the post-observation, we also have pre-observation. In the box in the middle, you have random assignment to a control group and an experimental group within already existing groups. So as you can see, there are dotted lines there separating basically three different groups of people. So maybe this is like different years in college. So at the top, you have first-year students, then you have second-year students, then you have third-year students. So those are already existing groups, but within those, you do some random assignment, and half of the participants in each of those existing groups are exposed to the X variable, and half of them are a control group. So that would still be considered a true experiment. The box you see on the right has 4 different groups, so random assignment into each of those groups, and the 2 rows at the top are basically, an experimental group and a control group, but you have both a pre and post observation. So I didn't include 1 and 2 in those notation, but that's basically assumed you have either a pre or post observation. And then in rows 3 and 4 of that design, it's the same, except there is no pre-observation. Why would you want to set up a study like this? Well, this is a specific type of true experiment called a Solomon 4-group design. You can Google that for more information if you'd like. But the reason that you would design a study like that is to basically test whether there's any effect of your pre-test. So sometimes, if it's like an academic test or an intelligence test, or even if it's a physical test where you might get better at the task that you're doing by taking it repeated times, you might design a study this way just to test whether having a pre-test actually affected the outcome of the study. And if so, that would be problematic, but at least you would know if you designed the study this way. So small n or single subject studies are studies that involve either one participant or a small number of participants, and you intervene as the researcher, you intervene after a period of baseline observation. So in this example, there are 4 baseline observations taken, then the manipulation is introduced, and then there are 4 more post observations. So this could be referring to one group of a small number of participants, or it could be just referring to one participant. It's basically just seeing if there's a change in the dependent variable O in response to that X variable that's introduced halfway through the observation period. An extraneous variable is one that's not related to the purpose of the study, but may affect the dependent variable. So if allowed to influence the dependent variable, an extraneous variable becomes a confounding variable where it's impossible to untangle the effects of the extraneous variable and the independent variable. In other words, you don't know if it's the independent variable that caused the change in the dependent variable, or if it's just some other third variable. So this is called the third variable problem. So this is just some terminology to be familiar with. And this is why, as I said earlier, in a true experiment, the researcher is motivated to try and control as many and keep constant as many of these possible extraneous variables as possible. And so this refers to the idea of experimental control, controlling extraneous variables to ensure that they don't confound the results of the study. So this enables the researcher to establish a cause and effect relationship between the IV and the DV. By randomly assigning participants into study groups, we've at least taken one step to ensure some experimental control. As I said earlier, that's helping to ensure that those two groups are as equivalent as possible, because they haven't chosen their group, they haven't volunteered to participate in one group or the other. There's not something that's different about them in terms of which group they've signed up for example. We've taken care of that by doing random assignment. Internal validity refers to the extent to which changes in the DV are associated with changes in the IV, as opposed to being affected by the other extraneous variables that might influence the study. So for example, let's say there's a study looking at the effect of a mindfulness program on stress. So participants complete the mindfulness program, but there are some participants who also attended counseling that's not part of the study. So if a change in stress is observed, can we attribute that to the mindfulness program? Well, in this case, it's possible that this additional counseling that some people are participating in outside of the study may be confounding the change in stress. So we don't know if the change in stress can be attributed to the mindfulness program or the counseling. So that's a problem for internal validity. Another type of validity is external validity. This refers to the degree to which the findings of a study can be generalized beyond the context of a study. So for example, we might design a study looking at what motivates children to participate in rec sports. On the basis of those results, can we conclude that what motivates children in recreational sports is also what motivates adults who play sports professionally? And I'm sure you would agree with me that that's probably not possible or it's probably not the same thing that motivates children that motivates adults. So, we can really only generalize the evidence from a study to the same population that we've included in the study. So that's an issue of external validity. I believe that is all for this video. Thanks and have a good day.